How are you? Thank you for starting the room. Can you hear me? Uh, um, uh, Let me write you. Can you? mm,
Yes.
Yes, you can
Thank
hear
you
me.
for.
Perfect.
Can you hear me?
If you could do me a favor, could you click on my profile
Oh.
picture and then make me a moderator so I can share a link and help you with with the if people want to raise their hand and ask a question. So when you click on my profile picture,
Yeah.
on the bottom there should be make moderator. Oh, perfect. Thank you so much. How are you today? Everything good?
Hello.
Hi,
So,
Victoria. How are you?
Hey, nice to see you.
Um, are you talking?
Me?
great.
No. Dr. Yanagisawa. I'm just checking
Good.
if we can hear
Good.
you well.
Yes. Good.
You're
Hey,
breaking up a
Fukuma.
little bit.
Welcome. So,
Yeah, we cannot hear you very well. Can everyone hear me? Is it on my side?
I can hear you, Katarina, and Dr. Yanagisawa. I cannot hear you very
yep.
well.
Hey. Sorry.
Oh, no problem.
Doctor, if you have any headphones on, sometimes that makes it more difficult to hear the speaker on Clubhouse. We find that it can work best with just using the speakerphone if that's possible.
Uh, can you hear me?
It's a little bit not too loud.
Too loud. Okay.
Okay. We'll start in 5 minutes. We still have a little bit of time, so we just add the topics to the room. Great. Hi, Abyss. You want to come up? Hi, everyone in the audience. We'll start in a few minutes. Thank you for coming. Hi, welcome, Dr. Fukuma. How are you today? Can you hear us well? We're just checking the.
Yes, I
If,
do. I hear
oh,
you very well. Sorry, my mic was off.
oh, perfect. No, we can hear you very well too.
That's good. Thank you.
Perfect. Hi, Abyss. Yeah, meet Abyss and Victoria. Victoria helps me moderates the room and helps me ask questions. And Abyss is also one of our valued members here.
Right.
Thank
Right.
you. I've just turned on some background music while we're waiting,
Yeah, we'll start
if
in
that's
three
okay.
minutes.
Really.
I've chosen this composer that I really love, Ryuichi Sakamoto. I thought it would be nice for this talk.
Is one of your colleagues in the audience? Do you want to invite him? Because I see, I don't know if you invited more people from your lab or from the paper. Please let me know. We can bring them up so they can also share.
Right. Thank you.
Welcome, Dr. Shah.
Hi Victoria, hi everyone.
Good evening, Dennis. Hello, Frank and Kirko. Come on up.
How's it going, guys and gals?
Kirko, I didn't really hear what you said.
I was just asking how's it going.
Oh, doing well. It's sunny out here right now.
Nice.
How about you?
Well, it's dark, but it's very warm, so I'm liking it.
I'll slowly start the room, and so thank you, Victoria, for the wonderful music. It was very relaxing.
It is. I love this composer. Thank
Yeah,
you.
it's very nice. You always have very nice music.
Thank you. It's recently discovered, but yeah, thank you. All right, go.
Okay. Welcome everyone to the Science Society. We are very honored to have our special guest here tonight, or probably wherever you are in the day, in the time of the day you are. And yeah, let me introduce you first our two guest speakers, Dr. Yanagisawa and Dr. Fukuma. They will be talking about their very interesting, amazing research here today. And Dr. Fukuma, he's a specially appointed assistant professor of neurosurgery department and of the Graduate School of Medicine in Osaka University in Japan. And he is in Dr. Yanagisawa's lab and the Department of Neurosurgery, also Osaka, Japan. And he is a professor in the Institute of Advanced Co-Creation Studies and neurosurgeon, MD, PhD. And prior to joining the institute, he was a lecturer in the Endowed Research Division of Clinical Neuroengineering at Osaka University, and he received his PhD in neurosurgery from Osaka University in 2009, and he was a postdoctoral researcher there afterwards. And he received a Young Science Prize from Max Japan in 2013. And the research is in clinical neurophysiology and clinical application of brain-machine interface and neurofeedback, which includes analysis of intracranial signals implanted in human patients. They are particularly interested in decoding and control of cortical information using big data of brain signals and human behavior. It's really an honor to have the two of you here. And if it's okay, Victoria would ask you a more general question in the beginning, and then the stage is yours to share your research. Is that good?
Uh, I asking me. Well, it's alright.
Yeah.
Yes, of course, yes.
Okay. Thank you, Victoria.
Thank you. Yes, thank you, Katarina, and thank you, Dr. Fukuma and Dr. Yanagisawa. We're so happy to have you here. We like to start with a general question, as Katarina mentioned, to give us, to maybe familiarize ourselves with you so that we can know a little bit about the researchers who are presenting, and we can know you more than beyond your research. And so if it's okay, my question is a two-part question, and so this can go to both of you.
Mm.
Reflecting on your experience in childhood or maybe later, can you recall when you realized a strong connection or maybe an attraction to science or scientific exploration? Maybe it was a teacher or an outing you were on, but something that made you feel that pull, that told you science was something that you really identified with. And then, can you share an overview of the path that has led you to the research that you're presenting here today? Thank you.
Uh, right. Well. Sorry, I couldn't get your point at the was the first question. Yeah, and I found with the second one.
First question.
Yeah, sorry. Yes.
When do you know when you first felt interested in science?
Oh, right. Right. Uh, well, it's quite a difficult question,
Yeah,
actually.
yeah, and it's okay
Yeah.
if it's.
Yeah. Well. Yeah. Well, actually, I was interested in research when I was quite young, and then I just get interested with human brain activities. So I started research with brain computer interface. Yeah, right.
Yeah.
Anyway, so is it okay?
So okay. Yeah, thank you for humoring us. And yeah, thank you so
Right.
much. We really appreciate that. And I don't know, perhaps Dr.
Uh,
Yanagisawa, would
can
you?
can can you
Yeah.
hear me? Okay.
Yes. So I
Thank you.
can hear you
So
so much
so
better.
because I'm a neurosurgeon, so I'm pretty much interested in to cure some patient, and basically we are interested in neuroscience to develop new tools to cure some neurological diseases. Actually, we are neurosurgeons, so we are so much interested in the invasive techniques to do actually, so there, so far we have not so much tools to recover the neurological function. So we are interested in the brain-machine interface to reconstruct the neurological function. So, uh, as I'm not quite sure when I have developed the scientific interest. I maybe I'm so much interested to uh, to contribute to to the to treat the patient in a young age. Maybe that's that was affected by my parents. I think. Uh, is it?
Thank you. Yes, it's fascinating to hear the different answers that people come and share with us because we all have such different experiences. And maybe somebody became interested. Often we hear that it was from our parents, or maybe it was an experience in a classroom. So,
Right.
thank you very much for sharing that and for reflecting. And if you're ready, then the stage is yours to share your research.
Right, thank you.
And I may say that our format is that you can present your research as you wish, and
Yeah,
after, then we can open up the stage to some friends who can can have a Q&A with you, some questions and answers.
right, okay, yeah.
Thank you.
Okay, so yeah, I'm Ryohei Fukuma, the first of this paper entitled Voluntary Control Semantic Neural Representations by Imagery with Conflicting Visual Stimulation. But first of all, I'd like to introduce background of this study. So, well, as the Dr. Anaxa said, we have been working on brain-computer interface and so-called BCI, and our purpose is to develop BCI that can be actually applied to patients. So, among many types of diseases that BCI can help the patients with well, ALS have strong needs for BCI because when ALS gets severe, patients gradually lose control of their muscles and finally they become locked in state. So that means also they have very good cognitive functions, they become paralyzed and unable to communicate with others. And actually, many researchers have been working on BCI so that the patients can communicate again with others. And actually, some researchers have already shown that with implantation of electrodes in their brains, the patients can use some spelling machines to communicate. Well, but there is some problem. These BCIs relies on the motor-related activity, where these motor-related activities are known to lost when ALS disease progress, and compared to the motor-related activity, vision-related activity is known to survive longer. So we focused on imagery-based BCI. So that's very, very background of this paper. So for the purpose of the BCI, we needed to solve some important questions. So, well, if I think you have some PDF or something. So please look at figure 1B and imagine the vision-based BCI is in use. So the patient is on the bed and the feedback monitor is placed in front of the patient. So first question is that if the patient can change their brain activities by visual imagery while looking at the different image on the feedback monitor. So, well, when we see something, for example, when we see human face, vision-related brain area called visual cortex activates with some special pattern, which we call neural representation. Interestingly, when we imagine same thing while we close our eyes, visual cortex is activated with similar pattern as if we were looking at the human face. But what will happen if we imagine while we open our eyes? So I think it's quite easy for you to imagine something while looking at someone's face. But the neural representation while looking at something while imagining different things has been poorly understood. And the second question is that if the patient can control the image in the feedback monitor by visual imagery. So we tackled these two questions in this paper. So first of all, we built a hypothesis because we know that the visual perception and visual imagery evoke similar neural representations in the visual cortex. Our hypothesis is that imagining an image would activate a neural representation of perceiving the imagined image even while watching a different image. So, well, let's consider how the imagery-based BCI works if this hypothesis is true. We first create a decoder to infer perceived image from the brain activity. And then this decoder is applied in the real-time decoding like a situation shown in figure 1b. At first, the feedback monitor shows some random image, but the feedback image on the monitor is updated every 250 milliseconds. So when the patient visually imagine an image for a certain category, the imagery should change the brain activity a little bit toward to the neural representation of perceiving the image of the category. So the feedback image become a little bit similar to the imagined one. Even if this change is very small, successive changes will eventually show the image representing the imagined category. This is what we expected for the imagery-based BCI. Then, let me introduce two key techniques we used. First one is the recording method of the brain activity. To record the brain activity, we used electrocorticogram, also known as intracranial EEG or ECOG. It's a EEG, but the electrodes are placed on the cortical surface of the brain and often used to find the focus of the epilepsy. So you can find the electrode locations in figure 1A. And the second technique is word-to-vec. Word-to-vec is a method to convert a word into a vector so that linear operation can be performed. Most famous example is that the vector operation of king minus man plus woman makes queen. Using the 1000 dimensional space acquired by a word-to-vec model, we performed decoding. Well, so let's go into the detail. First, patients were shown with the 60 minutes videos consisting of various kind of scenes such as humans, animals, landscape, space, and food, and so on. You can find these scenes in the figure 2. Of course, we recorded the ECOG while they watched the videos. And from the videos, we created 1000 dimensional vectors, which we call scene vectors. Every 1 second, image was cropped from the videos and annotated by volunteers. The annotations were divided into nouns, verbs, and adjectives, and then they were converted into 1000 dimensional vectors for each. The vectors of one scene were averaged to create a scene vector. Figure 1b shows the results of the principal component analysis to the 3600 vectors. Well, because we have 1 hour videos. The horizontal and vertical axis denote first and second principal components of each scene. Roughly speaking, first component meant human face versus others, and second component meant word versus landscape. For these three categories, well, I mean word, landscape, and human face, we selected 50 scenes each. The selection was based on the highest correlation coefficient of the scene vector with the vector for word, landscape, or human face. Well, for the vector of the human face, we just average the vector for human and vector for face. These selected scenes are shown with the color dots in figure 2b. and the average brain activity in the high gamma band, while the high gamma band is frequency between 80 to 150 hertz. And so the average brain activity in the high gamma band, while the patient was shown with these scenes, are shown in the figure 2C. Well, you can see some activation in the visual areas shown is the green and the blue color. Each denotes the early visual areas and higher visual areas. And the electrode that activate differently by the categories also shown in the rightmost panel in the figure 2C. So the electrodes in these higher and early visual areas responded differently to the scenes of the different categories. Then we perform the decoding analysis. From the high gamma band brain activity, we infer the scene vectors using regressions. The result is shown in figure 3. Figure 3a, the inferred vectors were converted into the PCS space acquired in the figure 2b, and we calculated the correlation coefficient between the values of the actual principal component and the values of the inferred principal components. The first component showed the highest correlation coefficient around 0.4. And we then performed the real-time feedback task shown in figure 4. And figure 4a shows the timeline of a trial. At first of the trial, patient was given with auditory instruction to display. So word, landscape, or human face. And the patient started visual imagination there. Then the feedback monitor started to show the feedback images. And in each trial, 32 feedback images were shown with an interval of 250 milliseconds. And the feedback image was selected from the cropped images of the stimulus videos based on the highest correlation coefficients between the scene vector and the vector inferred in the real time. So feedback images of representative trials are shown in figure 5a. And we calculated the decoding accuracy again based on the correlation coefficients for each inferred vector for one single feedback image. Correlation coefficient of the inferred vector was calculated with the vector of word, landscape, and human face. Because it's a three-choice task among the three categories, if the highest correlation coefficient was achieved with the instructed category in the trial, the prediction was considered to be correct. Actually, the red bars under the image in figure 5a denotes correct prediction. Timeline of the accuracy is also shown in figure 5c. And to evaluate the overall accuracy, we did the similar three-choice evaluation using the correlation coefficients averaged among the 32 feedback images in the trial. The accuracy was in the range of the 41.76% to 50%, where the chance level accuracy was 33.3%. And all 4 patients participated in this real-time feedback task showed the significant accuracies. So that means the patients could control the BCI using the Imagery. But toward which direction did they control? To evaluate this point, we concatenated all the inferred vectors and the vectors of the instructions during the real-time feedback task and again compared them in the PCA space. The correlation coefficient for each component is shown in figure 5F. And well, I think it's a bit interesting. So component 1 shows the lower correlation coefficient compared to component 2. So the relation is different if you compare the figure with the figure 3A. And then we performed another task to evaluate how the neural representation actually changed due to the visual imagery. So experimental paradigm of this task is shown in figure 6A. At first, the patients are shown with an image of a landscape or word. During this period, they were instructed to remember the image. We call this period as the non-imagery period. And then another image from the another category was shown. So if patients were first shown with the landscape image as the first non-imagery period, they were then shown with the word image. And this time, the patients were instructed to visually imagine the first image while watching the second image. And we call this period as the imagery period. When we compare the high gamma brain activity during these two periods, we found that the imagery decreased the power in the early visual areas. So it's shown in figure 6C. Using the decoder similarly trained to the real-time one, we decoded the brain activity of these two periods. And this result is shown in figure 7A. And blue and red points denote the image category the patient was shown with. Blue one is the landscape, and the red one is the word. And horizontal and vertical axis denote the correlation coefficient. Correlation coefficient of the inferred vector with the vector of landscape. Correlation coefficient between the inferred vector and the vector of landscape or word, respectively. So please look at the left panel of the figure 7A. So when patients are simply looking at image, red and blue points distributed like this. And if we could perform some perfect decoding, the red points are expected to go over the diagonal line, and blue points are expected under the diagonal line. Anyway, so please compare it to the right panel. The blue point moved upward. So that means when a patient imagine a word image while watching the landscape image, the correlation coefficient between the inferred vector and the word vector increased. This difference must be caused by the visual imagery. We named it as modulation and evaluated this modulation for each time window in the two periods. And then please look at figure 7C. The modulation towards word, I mean the difference caused by the imagery of word image while watching the landscape images are significant in the two time windows, that's 0 to 1 second and 1 to 2 second. And the modulation for landscape was significant for the 0.5 to 1.5 second time window. We did the same analysis using electrode in the higher and early visual areas. Results are shown in the figure 7E. The modulation seems to be larger in higher visual area compared to the early visual area. So, right. So far, that's the end of the all experiments. So we have shown that with these experiments, we have shown that the patient could really control the imagery-based BCI, and also shown that the imagining an image actually activated the neural representation of perceiving the imagined image, even while watching a different image. In other words, the hypothesis was true, at least for word and landscape category. And I think there are many things that can be discussed, but among them, I want to mention the one point. I think that's interesting and important point. So, as I just mentioned before, the difference between the figure 3a and figure 5f. So, the first component showed the highest decoding accuracy for the offline analysis. Well, I mean, when the patient was not in the real time without real time feedback. But when the decoder was using the real time feedback task, the accuracy decreased a lot. So maybe the direction along which the decoder can infer easily do not always mean that patients could control the feedback along the direction. So to achieve good decoding method or decoding space, well, the one we use Wattbeck, probably we cannot rely on the accuracy of the offline analysis, but we need to perform actual real-time feedback task and see the accuracy. Right, so basically that's it. So is there any questions?
Thank you so much for presenting your so interesting work. It really amazed me when I read your paper that you could distinguish like that you could distinguish so well between the imagined image and the image that patients were seeing, and it will be really great for people that have locked-in syndrome or ALS patients, as you mentioned in the paper. It's amazing. So, yeah, please flash your mics if you have a question. Yeah, Abyss, go ahead.
Okay. Ohayo gozaimasu.
おはようございます。
Yeah. So yeah, this is really fascinating, and I think like this kind of takes in the brain computer interface to like a whole new level. Because like so far, I think that we're kind of dependent on the sort of a very highly invasive motor cortex implants to essentially decode responses. But this, I think, is like really, really promising. The fact that it's ECOG and uh, has like minimal damage to the brain. That being said, I do have a couple of questions. First one being, you mentioned something about Word2Vec, and it seems like there is a lot of bias when you're doing Word2Vec, especially like when you're doing um, uh, trying to calculate or approximate dimensions, like you just mentioned, like for example, the distance between man and woman and king queen should be similar. I think that that's how Word2Vec essentially encodes. Do you see that same observation when you're measuring from the uh, like the like the area of the brain basically uh, like do you have like some kind of similarity between the two, how you do the word to vec to say like discerning faces of different genders or different discerning between different landscapes? That would be my first question.
So, uh, sorry. So, do you mean the what Beck has? Sorry. Mm, mm, mm.
Abyss, do you want to repeat that? Maybe?
Yeah,
Yeah,
sure. I
sorry.
can repeat that. So what I mean is that when we're doing word to vec,
Mm,
um, especially from machine learning point of view, we're
right.
trying to um, at least like project our understanding so that our system can understand it, can give us better accuracy. I guess my question is, by using word to vec approach, are you using some kind of or projecting your own bias into measuring the cortical activity? Does that make sense? I can rephrase that if needed.
Well, so well, sorry, I'm not sure if it's answering to your question, but the what Beck is well, so as a research using the fMRI shows that what Beck already shows that what Beck is can be used to brain decoding, and when when so, from the brain activities they show that the content of the visual perception, and I think some related feeling or something, and
Hi. Can I add something?
yes,
Actually,
please.
so I think that there are some biases using the word to back. I think there are two biases in here. One is the word to back itself. So word to back has the relation of the words among them. So and that was learned from the Wikipedia. I mean the natural language sentences. So there is some the biases of the relation in the word and word to back itself. And also we made the annotations of each image by the annotators. So the human annotator made sentences to describe the scenes. So that makes some biases. I mean the so so human bias and word to back itself bias. So but actually, maybe he did not explain, but we tried some several other method. I mean, several other representation space, but among them, this Wall-to-Back representation space was the best to be controlled so far. So I think that yeah, it depends. That our result depends on the representation space itself, and we need to find some good space to fit the brain activity, or especially the perception and imagery. So we are not quite sure what kind of feature or what kind of property is necessary to create such good representation space, but so far it's working well. Uh, yeah, is it
Got it.
clear?
Yeah,
Yeah,
that's actually very clear. Thank you. Yep.
great.
And my second question was, there is a condition. Well, technically, it's not a pathology, but there is a condition called aphantasia, where people are unable to imagine things. I don't know if that showed up in your, at least like if you try to address it as a potential problem when people go back to like reimagining the scenes that were they were given, so that you can devise a very stable and robust kind of BCI based on the visual system.
Oh, right. So you mean the so these kind? Do you mean that these kind of patients, well,
Yeah, so
cannot use imagery to control? Uh,
yeah, so they cannot actually visualize things based on physical cues. And
right.
for some reason, they may not actually kind of create this visual manifestation of what they saw and what they heard. It's not a pathology, like I said. I think it has primarily to do with the fusiform gyrus, but I'm just wondering if that kind of creates some bottleneck to do a visual cortex BCI.
All right. Right. Well,
So you mean the difference of the imagery, the ability to imagine something? So
May I jump in and explain about it?
yeah, yeah,
Because there was a research, first of all, thank you so much for the fascinating research. There was a research released recently, and some of the researchers, they found that the people who are experiencing aphasia, actually, that was about the contraction of the pupil of the eyes, through the light and dark pattern, because they cannot have a visualization. And I think that abyss means that, did you find any further information from your research that it can be related? Because they cannot have a visualization. And when they just put the pattern of the light and dark, they just notice that they don't have any reaction towards to it.
oh yeah. We haven't actually the so evaluate the so the I'm not quite sure the patient. I mean the patient cannot this imagine something.
Yes, basically they just explain that
Um,
through the light and dark, there is a different, I mean,
what
with the what, Katerina?
I think Dr. Yanagisawa is saying that they didn't analyze data from patients that have this difficulty, so they cannot answer the question.
Yeah, basically that's true. But yeah, so but of course it depends on there are some differences of the ability to imagine something. So some patient looks difficult to imagining. So someone says that he or she cannot imagine anything. So that that's a very difficult part. But in in uh, in our system, so BCI is a kind of closed loop system. So the patient can learn how to control the presented image by controlling their brain activities. That's the simple explanation of our system. So although we have instructed to imagine something, they might can control their brain activity by other strategy something. So it's we are not quite sure so far we cannot say that they can control the system without imagery, but it might be possible to control the by some other strategies without visual imagery or something. It,
Yeah, thank you.
yeah,
Yeah,
Um,
thank you.
thank you. Um, anyone else has questions with some?
I want to ask my question if
Oh,
it's possible. So my question is about your, samples actually, from E1 to E21 with epilepsy. I was just wondering, those people have a genetical epilepsy, or it just happened, for example, from the TBI or any kind of brain injury? This is my first question.
yeah, actually, I should answer to this question. So, most of the patients are focal cortical dysplasia. So they have some genetically some abnormal brain regions around the visual or occipital or temporal cortex, and yeah, I think one patient had the some trauma, but I think one, two, four. Yeah, yeah. I think the E1 to E4 were all FCD. I guess. Yeah.
And is there any kind of brain asymmetrical between the patient, or did you evaluate that or not?
Asymmetrical. Yeah, I think one patient had kind of asymmetrical, a little bit atrophic brain in occipital area. 福間君 do you remember that the E1 to E4 has the patient?
Sorry, I don't really remember it.
Yeah, I think the E1 to E4 has no such asymmetry, but we recorded all 17 patients. Among the patient, yeah, we have some asymmetrical brain. Yeah, patient with asymmetrical brain.
Thank you.
Yeah.
Wissam, did you have a question?
No, I'm just listening. I came in a little late, but I'm definitely gonna catch the replay. But I just ran a room for, I was presenting for like 3 hours, so a little tired.
Oh,
But thanks for the room. This paper is super interesting. I've been glancing at it, so I'm glad you've set this up, and I'll definitely catch up on the replay.
yeah, sure. Thank you. Frank, Denise, did you have any questions? Okay.
Uh,
Yeah, go ahead.
uh, I have a small question regarding the algorithm they use. I saw PCA. Are you considering any other learning algorithms in your work?
So what did you ask? So is our so applying PCA to something. So sorry, please repeat your question.
Yes, I saw. I only had a chance to look through your paper briefly, so I haven't read in detail, but I do catch the keyword you're using the algorithm PCA.
Yes.
Yeah, I was wondering, curious, are you considering other similar machine learning algorithm as well as a comparison?
No. So well, for the decoding itself, we perform the ridge regressions, and PCA is well just kind of to show the clear result. Yeah, we actually we want to evaluate the how the space, well, so what big space with the 3600 Shin vectors, what kind of so well I want to evaluate the space itself and the how the subject controlled the feedback images within this space. So we used PCA, but the yeah.
So
So
Dr. Fukuma used the PCA to represent uh, the how representation space is, but he also applied the TSNE to make the clustering uh, visualization of the representation space. Could, could you explain the difference?
right. So yeah, so for the visualization, I perform the TSNE. That's as a method to embed the high dimensional space into the very very small space with a very very small dimensions. So and the well, actually the result is shown in the supplemental figure, I think. And the when I perform the visualization with the figure like the visualization of the 3600 Shin vectors like the figure 2b, well, I get very very nice clustering, and each cluster contain similar meaning. So scenes with the landscape made nice clusters, and scenes with animals made another nice clusters. So well, from these results, I could say that the scene vector capture the semantic information nicely.
Yeah. And also,
Yeah.
if I can add some few things, in doing BCI, PCA is like pretty much this sort of the standard. As long as you can capture much of the variance, you can apply PCA and just play around with the two principal components. That would reduce a lot of dimensional hectic process bed, and taste needs as well is like a really good way to uh, essentially reduce the dimensions. But if you have features that seem to have some kind of correlation, you can reduce them in two dimensions so that you can get you know equal space, or at least like reduce the spacing between similar features. So yeah, I just wanted to add that up. Great explanation.
Oh, thank you very much.
So,
I
by the way, yeah.
yeah,
Uh,
go ahead.
Ah, so one thing I need to add maybe, so although we used PCA to the visualization, but we didn't do the machine learning in the PCA space. I mean, we did not reduce the dimension to make the decoder or to make the feedback. So the patient are controlling the 1000 dimensional space even in a closed loop situation. Sorry.
Yes, I understand. Thank you, for all the answers. Usually, when if there's a need, because sometimes the data lives in a very sophisticated higher dimension, so sometimes a researcher will augment their linear reduction algorithm with the nonlinear ones. Yeah, so I was just curious. Yeah.
Yeah, actually, we thought once to whether the control becomes better if we restrict the low dimensional space. So we just applied 2 or 3 dimension in the control space. But unfortunately or interestingly, it was not so much good result. I mean, the patient more easily controlled in a 1000 dimensional space compared to the 2 dimensional to 3 dimensional. So I'm not quite sure the reason, but I think that this 1000 dimensional space in the world 2 space has the meaning as itself. So the restricted to 2D or 3D PCA component has losing is losing some more information. So I think that caused the controllability.
Yes, probably, there'll be very interesting data to be extracted, right? So if there's a embedded manifold type of higher dimensional structure in your data, then it's a gold mine, yeah, for further extractions. Yeah.
Yeah, thank you so much. Dr. Fukuma, do you have any comments on that?
Uh, no. Well, well, I have no additional comment on this.
I thought you mentioned later in the discussion about the different differences between the gamma activity and the alpha beta activity that convey the top-down signals, and the that they change over time, if I understand it right, and that the imagery task was modulated by the gamma band. Is that correct?
Uh, Well, so in discussion, yes, we discussed with yeah about this point. Yes, gamma sheet and gamma band activity. Well, previous studies says that the sheet and gamma activity conveys the bottom-up information. So that's actually information about with the of the perceiving image, and alpha beta activity conveys the top-down information. So we think that's the information about imagery itself. So and the well, actually in our studies, we decoded only in high gamma band because it has the highest accuracy compared to others. And yeah, but the yeah, I think it's consistent with the previous study because they say that the gamma band activity conveys perception information and actually receive the highest accuracy. And yeah, and actually some studies says that there is some coupling between the low frequency band and high frequency band, cross frequency coupling. So maybe through this cross frequency coupling, the modulation, so I mean the imagery affect the activity in the high gamma band, conveying the bottom up information. Well, but it's just a speculation because we haven't performed that kind of analysis.
Yeah, that's really interesting to me. Um, do you think that if you record more and more data, that maybe one day, I'm not sure how comparable the EEG data, like purely EEG data, would be, but do you think if you train enough with your more clean data from the implanted BCI, do you think you could train basically with that data, EEG data set, and you could get clean the data basically to get information that's comparable with the quality you have right now with the implants one day?
Actually, I don't think so because well, as you know, EEG, so scalp EEG can only capture information with the frequency up to like maybe 30, 40 or 50. And with, well, I think I have some result for that. Yeah, so if you see the figure 2A, that's replicability of the brain activity. So, well, as I thought, the patient was shown with the 60 minute video, but actually we have shown them another video consisting of a whole repetition of the 2.5 minutes videos, and we just evaluated how the brain activity replicate between this repetition. So if the color is high, the brain activity was similar between the repetition of the videos. But if you see the alpha or beta map, the replicability itself is very very low. And well, and I think if you see the supplementary figure, I think you can find some decoding result with alpha or beta band, and it's much worse. So, because the EEG cannot capture this high frequency activity like high gamma or low gamma, I think it's difficult.
But that depends on the sensor, I guess. So maybe that it's the problem of signal to noise ratio. So if the signal is higher, it's easy to decode. But if the noise is small, it's also the high signal to noise ratio. So if we can reduce the noise, if you can develop the new sensors to be attached to the scalp, which can reduce the noise, we might record the high gamma activities. So, for example, if we can add or repeat the same stimulus several times, and if we can average the activity for the same stimulus, we can get some high gamma activities even in a low signal to noise ratio. But so but in this case, we are controlling the the, the in a closed loop online situation. So it's difficult to use the multiple stimulus or average of the multiple stimulus. So so yeah, but it depends on the sensors. So if we can develop the nice cleaner, a nice electrode to get the high signal to noise ratio, yeah, we can develop that kind of non-invasive PCI.
Thank you so much. Yeah, I think for places around the world where we don't have so many neurosurgeons and where it's not that easy to get a major surgery, I think that would be very important. But I think for our developed countries, this is probably the better solution. So thank you.
Yeah, thank you. Great.
Does anyone else has more questions? Please raise your hand. We are almost the hour is almost up. So if you have a last question, please go ahead. If not, I'll ask. Um, another question. Are you I wanted to ask, are you planning to also use this for not just the visual system, maybe for auditory or for speech? The same method with people that have, or maybe even moving object with your mind, basically. Are you planning, or are you doing going into more sensory motor um, areas with this technology?
Yes. Well, I agree. It's very interesting to do similar thing with the auditory or maybe some text text on the screen. Yeah, but yeah, problem is that how we can create nice feedback. That's the yeah basically problem. But yeah, it's very interesting to extend this research to other modalities. Yeah.
Yeah, we would like to make some multimodal feedback. Basically that people can image some concept. So uh, 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 that the same concept has the different modalities, something like auditory or visual. So we would like to decode and feedback to control that concept using this kind of similar method. So, but yeah, actually, the yeah, there are some problems, technical problems so far, but we are now trying to several things. Yeah,
Oh, that's really exciting. Yeah, I'm looking forward to follow your research and yeah,
yeah.
finding out what's next.
Thank you. That's great. Yeah, but it's very interesting to know that kind of yeah. There are so much interest in this in BCI, so I'm very happy to hear this question. Thank you.
Yeah, it's really amazing. It's yeah, amazing what you were able to do with this technology. I really find it very fascinating. So thank you so much for taking the time and being here and sharing your knowledge and with us and answering our questions. So we really all appreciate it very much. And I hope you'll enjoy the rest of your day.
Yeah, thank you so much. It's my great pleasure to be here and to share knowledge. Thank you so much for this opportunity.
Yeah, I hope you come back with when you have updates and new projects to share with us.
Thank you so much.
どうもありがとうございます。
ありがとうございます。
ありがとうございます。
It's so similar to the Portuguese thank you. Obrigado. It's in Portuguese. So it's very
Obrigado.
yeah, it's very interesting.
ありが
Obrigado. Okay, great. Thank you everyone for coming and for asking questions, and thank you again for sharing your amazing research. And have a great day, evening, morning, wherever you are. And please follow the Science Society if you like rooms like this with invited guest speakers. And yeah, I hope I hear you all back sometime soon. Thank you.
Thank you very
Thank
much.
you.
Thank
Thank you.
you.
Bye.
Bye.
Bye everyone.